Welcome back again to the lecture. So, we are going to start the module 3 of this course. Module 3. So, in this module we will be discussing about a special class of differential equations, namely linear ODEs, and we restrict ourselves to the first order and second order. We will also study the first order linear systems, which includes the nth order equations, nth order linear equations. And what we have seen in module 1 and module 2, module 1 you have seen some interesting examples, and module 2 you have seen the preliminaries required for this course. So, that two are the kind of elementary discussions, and from here onwards we start our actual study of ordinary differential equations. So, we thought initially, before going to the existence uniqueness theory, we will straight away come to the some of the easier differential equations known as linear ODEs, which we will explain what are linear ODEs, and we already classified differential equations into first order wise, first order, second order, third order, etc. It is another classification of differential equations what are linear and non-linear, linear, non-linear. Now, you are already familiar quite a bit what are linear and what are non-linear, but we specify more about it. In this first when we discuss this linear ODEs, we will also discuss something what are called exact differential equations, exact differential equations. So, this is the planned differential equations and this is the plan in this module. Maybe we will finish this module in 5 or 4 or 6 lectures. Okay. And so, what is so let me begin with before thing. So, what is the general first order, since the first lecture essentially on ODEs after the preliminaries examples. So, a general differential equation, general differential equation of first order. So, we will first think that first order differential, first order. So, we will start with the first order ODEs. So, a differential equation of first order takes the form, this is the more thing, takes the form f of t y prime equal to 0, where what is y equal to yt is the unknown function to be determined, unknown function to be determined, and you can t is the independent variable, t is the independent variable. Now, you know what is the meaning of independent, dependent, all concepts are already understood in the preliminaries, and y prime I denote for dy by dt. So, there are different notations we will see for the first derivative y prime dy by dt. This also you may see that y dot of t. So, you will see all these things according to the convenience, comfort level, and the way it is written, you will use various notations. As remarked in the introduction, this itself is probably have difficulties in dealing with that. Probably we will see some of them as we go along, but what we will be seeing in most of our thing, a special type from here, what are called where y prime is equal to some sort of f of t by 4. These are all form, this f is not necessarily this f, okay, this is a general form here. This is more general, this one is more general, this is more general, because if you are given in this form, it is not necessary that from y prime you can solve this equation. This is, if you think that this is an equation in t y y prime, it is in general you will not be able to solve it in a nice way y prime to write this one. So, this is a very special class of equations. Okay. So, we will okay. All right. So, what is, how does an initial value problem looks like? So, you have the initial value problem. So, an initial value problem for this looks like y prime is equal to f of t y and y at t naught is equal to y naught. So, you see this is the initial value problem. Okay. So, you have to study initial value problem. The regarding the existence, uniqueness you will study later, existence, uniqueness will be studied later, uniqueness will be studied later. Okay. We will not will that, this we will see later. That is in another module, that regarding the existence, about the conditions under which f, which you have already introduced in our preliminaries, like the continuity, Lipschitz continuity, all that, and you will see in fact different methods to study this equation. And the more easier one, again I remarked, when is the y prime is equal to f of t. So, the function f do not depend on y, and this is an easier problem which we will discuss soon. Even this problem, solving this equation, this is essentially dy by dt equal to f t, and this is nothing but your this is, I call it, the integral calculus problem. We will come to that, integral calculus. You see, that is the easiest one of the integral calculus is developed to solve the one of the easiest differential equation. So, that is what you will be doing it in this one, but we will explain to you little more about it. So, when you solve this differential equation, you know that dy by dt is equal to, and you write your solution y of t is equal to, in the initial value problem if you want, integral t naught to t. Let me use another f of s dr plus c. So, you have a constant, and if you want to see is uniquely determined, is uniquely determined if y equal to at t naught is equal to y naught specified, if you do that. Okay. So, this is what we are going to do it here. All right. As I said, in addition to this order classification, you have the classification in terms of linear. So, what do you basically mean by linear? So, you can think that when you given this functional relation between the independent variable y and y prime, viewing t as a parameter, if you view this function y is equal to L of y prime, you are exactly demanding L is linear. Now, you know linearity from the, what is the concept of linearity? L is linear with respect to both y and y prime. Note, we do not demand linearity in t. Linearity in t. So, what is linearity? Linearity basically tells you, if you have L of alpha y1 plus beta y2, two functions y prime, you need linearity alpha into L of y1 y prime plus beta L of y2 y prime, and similarly L of y alpha y1 prime alpha y prime plus beta y2 prime is equal to alpha into L of y1 prime plus beta L of y2 prime. So, you see the linearity, and if you look at the linear look at the linear algebra preliminaries which you have studied, and probably I can leave it as an exercise that f takes the form, the general form of f can be written. Once you have this linearity property, you can write f takes the form f of t y prime of the form p naught of t dy by dt, that is y prime plus p1 of t into y of t. So, you get a homogeneous equation. This is called a homogeneous equation, we call it, we get the homogeneous equation, a general form of homogeneous equation which is linear first order of the form. This is the homogeneous equation p naught t dy by dt plus p1 of t y equal to 0, and if you put a non-homogeneous term on the right, so your non-homogeneous term, non-homogeneous equation, again linear first order, will take the form p naught of t dy by dt plus p1 of t y equal to, or we use it p only here, just we take p of t, we will take p of t here equal to qt, you see. So, this is the first general form first order homogeneous equation, and this one the first order non-homogeneous equation. As you soon see, we will not be considering in this generality again, because as I said in the previous few minutes back, having coefficients have trouble. So, we will see one example coefficients. We go to the previous slide. As I said, we have described this, we will be considering only this equation. We are not considering coefficients thing. The trouble comes when that coefficients of y prime vanishes. If the y prime, the coefficient of y prime, even if it is a function of t, does not vanish, you can take it here by dividing it. So, the problem comes when there is a vanishing coefficients in the highest order derivative. So, if you consider a highest or second order derivative differential equation, and if you have a vanishing coefficients in that highest derivative, then it can cause problems for your differential equation and initial value problem, and such equations are normally categorized in the class of singular equations. So, we will you may see one or two examples later. So, we will consider this regular type of equations, dy by dt plus pt y is equal to qt. So, this is the equation we are going to completely understand in this lecture. A complete understanding of this equation, we will do it here. So, we will start with an example. Where is that trouble? You will see these examples again and again in future, But let me start with an example, very simple example. When there is a vanishing coefficient, the singular type equation, so I will take t dy by dt minus 2y equal to 0. You want to solve this equation. Let us initial condition. How do you solve it? You follow your normal procedure. When you follow your normal procedure, you write from here. Now you know the meaning of what is that, which we explained in the beginning, the change of variable formula. So this is nothing but the dy by dt is equal to 2t dt. You integrate, you do everything, that is a simple integration, and that I will not do the calculation here. You can write log mod y, log mod t and all that. At the end of it, you will get y is equal to c into t square. So that is a general solution, you will get it for this equation. Now look at the initial value problem, a simple initial. What are these one? These are nothing but parabolae. So if you plot this parabola, all these are all parabolas irrespective of c, it is all passing through the region, because when t equal to 0, y is also equal to 0. So you will have, if you fix your t, you will have one parabola. So this may be something like y equal to c1 t square. If you choose another one, you will have another parabola. This may be y equal to, see, it may not look like parabola, but it is a parabolas. Mathematicians can anyway imagine parabola, so that is not a problem. So you will get a different parabola. You see, all these trajectories pass through the origin. So I put an initial value problem, this problem, this is my initial value problem 1, together with my initial conditions y at 0 equal to 0, together with my initial conditions, equation 1 with y at 0 is equal to y 0, then for any c y equal to c t square are solutions. So what does that shows that? It is against our well-postness criteria, basically, that there are infinitely many solutions. You see, even such a linear first order equation, the situation is not that easy to handle, infinitely many solutions. So now you understand why we planning to consider only this term. So this can create even such a simple first order linear equation, and it vanishes only at one point. You have a thing, you have infinitely many solutions with the PDE with these initial conditions. On the other hand, if I put 1 with y 0 is equal to 0, y 0 equal to 2 or 1, say I put 1 here, I put 1 here, this is 1, y 0, there are no solutions, there is no solution. So you have a situation for the same problem, existence of infinitely many solutions and existence of no solution. You can also have a situation, if I take the same problem, if I try to avoid t naught, say greater than 0 for example, and if I consider this PDE, this let me call it this PDE 1, the PDE, the ODE 1, not PDE, sorry, this ODE together with initial condition y t naught is equal to any number, does not matter, y naught. Then if I put t equal to t naught here, I get y equal to y naught, I get my c equal to y naught by t naught square, yt is equal to y naught by t naught square, t square is the unique solution. So you see, so you have the unique solution. If I move away, this is for all t greater than t naught. So you have solutions for unique solution for this initial problem. You have a situation when you are the initial conditions are prescribed at that singular point, then you have the infinitely many solution situation. You also have a situation where there are no solutions. So, that is why we do not consider for the time being in this first order case. You may see something later, but we will try to restrict to this situation. Okay. So, we will go to now to understand these first order equations. So, we will have first order. You want to solve it now, first order equation. We are going to this is equation. So, this is our equation. For the simplicity I write it, L of y prime is equal to dy by dt plus pty is equal to 0. So, let me start with the homogeneous case, then we will come to non-homogeneous case. Homogeneous case to start with, this is the non-homogeneous equation. You want to understand that. So, let us take the simple case. What is a simple case? I am keep on telling you is the integral calculus problem. Let me spend 2 minutes, because I want you to see that integral calculus is developed in the process of solving ordinary differential equation, which quite often ignored, because you study integral calculus in a different way and ODE is in a different subject. This is, so you have to, when your integral ODE course is there, you have to begin from the integral calculus problem. So, what is the integral calculus problem? Given f equal to, as a function of t alone, there is no y, you want to solve, want to find the antiderivative, that all of you know it, dy by dt is equal to f of t. You want to find the antiderivative. So, the solution to this is essentially the basically the development of integral calculus, and which essentially end with what is a famous theorem called the fundamental theorem of calculus. So, I am not going to write the fundamental theorem of calculus which you are familiar, but essentially what I am stating, if you rewrite it, you get the fundamental theorem of calculus. So, I will recall some of these things. So, when this problem, so you assume f is continuous, that is a minimum assumption, assume f is continuous. How do you solve this equation? That is what the probably you know the development of integration or development of the concept of area. You have to also understand that integral calculus problem actually unifies 3 fundamental problems in the thing: the tangent problem, antiderivative problem and area problem. So, the fundamental theorem basically connects these 3 in the 3 important problems like tangent problem, antiderivative or antitangent problem and the area problem. So, suppose this is given in with an interval, say AB. Suppose this problem you want to solve it in AB, you want to, or any other things. How do you solve this equation? That is concept of area, which I forgot and which I am not going to give it here. What you do is that you define the integral via the concept of area, which all of you know it. So, you have A of B, you define the area concept, what Cauchy essentially done that through Cauchy's sum, what do you call it? I do not introduce it here. Now, you go back to your integral calculus integration which you have developed, you define the in the thing. What you have done is that this area, if f is a continuous function, the area exists, that you prove it by dividing this region into small pieces and defining the Cauchy sum, show that the Cauchy sum converges and which comes in. And this area is basically you call it integral a to b or t naught to t if you want it. If this you call it t naught, you call it t naught to b. This is basically just like dy by dt is a notation. I told you this is just a symbolic notation for the area, symbolic notation for area, or you can, or the limit of Cauchy sums, limit of Cauchy sums. All this you have to be careful while you, or you rather you have to understand it that way, Cauchy sum. Okay. So, that way you define this area concept. So, what you and how do you proceed further, how do you solve this problem? So, let me complete that problem. So, you have this area. So, you have your T naught given here, and now you know the area. The function f is continuous in this entire interval, whatever it is, you put any t here. The function is continuous there, the function is continuous here also in t naught to t. So, you can define f, you can define capital F of t. The after defining the integration via the area, you can capital N of t is equal to t naught to t f of s ds. You see. Then the next step one proves in integral calculus, show that f is differentiable, f is differentiable and compute its derivative df by dt equal to, if you compute this one, you can see that this is nothing but f of t. So, you basically get to the existence part. So, so that gives you the existence part. Therefore, existence you get it yt equal to, not for the initial value problem, for the solution to the differential equation, yt equal to ft solves dy by dt equal to f of t. You see, you have a solution. So, this is the first part of the fundamental theorem of calculus essentially. After that, there is one important fact, the second part, this is also you need it in the fundamental theorem of calculus, or you put it in the form which you know it. This tells you that if f is differentiable, and f prime of t equal to 0 for all t, then this implies, this is non trivial fact actually, one need to prove it or understand it. So, that is why it is a, I am writing down the fundamental theorem calculus, all the development in 3 parts. One is this development of this one, development of defining this appropriately using Cauchy sum and showing this one. And then the second part is this, if there is any differentiable function for which f prime of t equal to 0 for all t, then f will be constant. The third part comes in the uniqueness aspect. We can write it when you put an initial value problem, the uniqueness comes into picture. You say the third part of the fundamental theorem part calculus is the crucial one, and probably that is the one you will be seeing it. So, this capital F is called the antiderivative, is called the antiderivative. The question is that, does there exist any other antiderivative? Does there exist any other antiderivative? That is the question. So, you have produced one, if you given an small f is continuous, if this function f is continuous, then you produced an antiderivative using the area. The next question what I am asking is that, is there any other antiderivative? Yes, you can immediately identify some antiderivative. what are the antiderivatives? You have one antiderivative and you add the any other f to given f t, you add any other c is also an antiderivative, also an antiderivative. Okay. So, you have one antiderivative produced via this one, whatever the Cauchy limits, and then if you add any constant, because the derivative of that constant is 0. So, if you take g is equal to then dg by dt is also equal to df by dt, and which is equal to f by here from here. So, the question is that answers the third part, no more antiderivatives. So, these three combined, no more antiderivative. These three together, whatever I said, existence of that antiderivative, f prime equal to 0 if implies, and no more antiderivatives together gives you your fundamental theorem of calculus. So, if I formulate it, no more this statement further, if g is any other antiderivative, if g is any other antiderivative, any other antiderivative, any other antiderivative, then g takes the form, gt equal to f we have defined earlier plus c. That means this has to be of the form ct plus t naught to t f of s ds. You see. So, what you have eventually proved is that if you combine all that one, you have a unique problem. There exists a unique solution to dy by dt is equal to dy by dt equal to f of t, y at t naught is equal to y naught. You see. So, the moment you fix your initial condition, the constant is fixed, because any solution to this form of this case where and your solution has to be of this form, and this c can be determined if you fix it. So, what is the solution? Your y t is given by y naught, c will be y naught in this case, integral t naught to t f of s ds. You see. You have that one. So, that is what the first thing. Now, my idea, I want to go to the next level. So, what is the next level? I want to understand my solution dy by dt linear. So, I am going to the next level, linear homogeneous. What is that? Plus pt of y, now there is equal to 0. I want to solve this equation. This again easy. The whole thing what I am going to do in this whole lecture, every first order linear equation in this form can be converted essentially to a problem of the integral calculus, and integral calculus problem has solution. So, we will do that now. As I said, we assume p continuous. If p is not continuous, p is continuous. We will continue. We will do that one. So, how do you go ahead with that? How do you solve this equation? So, I want to solve it. This is easy, which all of you know it, but let me complete it. So, you have dy by dt is equal to minus pt y. So, if you solve this equation, bring y here, t there, minus pt dt. So, you know that, and take logarithm. I told you when you take log. So, let me recall what I have done in the introduction. What you get is only mod t. So, you will get something c naught e power minus integral of pt dt. So, you see. So, how did you remove? If you recall my introductory lectures, anyway let me state once more that one that was in the introduction. So, state then how do you remove this modulus? To remove this modulus, I will bring my exponential term here, integral of pt dt is equal to some constant. You see. Now, this is a continuous function. And this is our exercise, which you probably would have done it by now. If you have a continuous function whose modulus is constant, that function itself will be constant, and the case here, because this is modulus, this is positive. So, you will get your solution y t is equal to e power c e power minus integral of p t dt. So, this is a general solution. So, you have your general solution. You see, you have your general solution in that form. Okay. So, what you have done is that, so you have a solution. So, you have your, in fact you represent, in fact if you want it as a simple exercise, I have produced that solution in that form. You can verify y defined by 1, this I call it 1, by 1 is indeed a solution, indeed a solution. So, you see these linear equations, the nonlinear equations you will study existence and uniqueness, and you can apply that general theory to here get the existence and uniqueness. But I am trying to show you in this case you do not need to appeal to that general theory to get existence uniqueness. So, you have a direct existence here. You can also get your uniqueness, which is what I will quickly refer now. Uniqueness of this equation, this is the equation, let me recall once again each time to get familiarized. So, you have p t y equal to 0 with y at t naught equal to y naught. So, one solution is y t equal to, if you put y t naught is equal to y naught, from here you get c equal to y naught, you get y naught into e power minus p t dt. I want to show the uniqueness. Very simple, very easy proof. Suppose z is another solution. Suppose z t is another solution. Of IVP, I call this IVP. Now, consider it is a simple thing. What do I want to prove it? I want to prove z t is equal to y t. Okay. So, this is a simple idea, y t is of this form. I want to prove z t equal to that one, bring it here, show that that product is constant, simple as it is. So, define, I want to do it here because it goes back to the one of the component of integral theorem of calculus. So, define x of t is equal to, the idea of considering is not the thing, z t into, you want to show z t is equal to y t contains y naught e power minus thing, that minus you bring it here. So, you have a p of t dt. So, this is of course you can define from, so maybe let me write it in a x t is equal to z t e power integral t naught to t p of s, or we use the same variable, it does not matter, p of t dt. Now, compute, this is a small exercise which you can do it, compute dx t by dt. It is a small exercise, you can do that, it is not difficult. All exercises if you do it at that time, it is easy. If you do not do it, the coming exercises will be more difficult. So, you can do dz by dt. Keep it in mind that zt is also a solution to your differential equation with the same initial conditions z at t naught is equal to y naught. So, when you differentiate you get that one, you differentiate this, you know what to get it, you can actually show that this is equal to 0, you see. And this is what I said, this is one of the components of your integral fundamental theorem of calculus in the integral calculus. The moment you have a function x t which is smooth continuous, here in fact differentiable, and if that derivative is 0, this will imply x t is a constant, x t is equal to c, a constant. This implies if x t is a constant, you get z at t is equal to this constant into e power t naught to t p of t dt. Now, use initial condition, use the initial condition z at t naught is equal to y naught. So, that implies your z at t, if you use this one you get c is y naught, you get z at t is equal to y naught e power integral t naught to t p of t dt. You see, this is nothing but your y t. So, you see you can very simple thing, you can get your existence and uniqueness directly from this equation. So, you can solve all these equations, it is an integration problem. So, the homogeneous first order linear equation is essentially solving an integral calculus problem. To see one example if you want it, many examples can be given, but you should start working with examples and exercises. So, suppose I have dy by dt plus a sin t y, sin t at y is equal to 0. Say y 0 you put some number, does not matter, just to show, but any function if you take, if you write down the solution, the only thing you have to see is that your computation of pt, that is all. If you want to write down your solution, if that function pt if that function pt is solvable, there is a minus sign here which I missed here, yeah, because you are taking this to here. So, there is a minus sign. So, the finding the solution of the homogeneous linear equation is essentially you want to integrate that one. So, you want to write your integral of y t and you can immediately find the solution. It is a question of finding the solution, your solution y t, and substitute your initial condition. So, I hope the answer is correct, but I am sure it will be correct because it is nothing, you have to integrate minus 1. You see, you can keep plenty of equations like that. To show you one equation where you may not be able to integrate, suppose I write the equation example, you will also have difficulty. Suppose I have an equation dy by dt plus e power t square t t into y equal to 0. So, all of you probably know that you cannot integrate this explicitly, you can write that integration exists, but there is no definite formula to write that one. So, you can only write your solution, you can write your solution y t is equal to the initial value will come 2 into e power minus integral t naught to t over t square dt. So, you see, so you cannot do more than that because there is no way of writing numerically. Yes, of course you can compute, you cannot it is not possible to write this write this integral explicitly. So, with that let me go to the non-homogeneous equation. Non-homogeneous equation. So, its life is very easy in all these things because it is nothing more to do than an integral calculus problem. So, what is your non-homogeneous equation? You have dy by dt plus Pty equal to Qt, okay. And then we assume of course PQ continuous. This is always our assumption, continuous, and you have your initial value problem. So, we will write that one. So, that what is your L of y here? So, L of y prime, if you want to do that one, L of y prime, the homogeneous part, d by dt. This is some important concept I want to eventually develop for my next lecture. You have Pt of y, you have a linearity here. So, you have this equation, this operator. The idea, if you look at the integral calculus problem, if you have d by dt of something is equal to f of t, it will become an integral calculus problem. So, if we can write or if we can find h t such that L of y prime equal to d by dt of h t. If we can do, we call it basically, these are called exact differential equation. We will give a precise definition of exact differential equations later, but the whole thing is that if it is possible to find such an SG, I am not claiming it is possible there such an HT exists, but if we are able to do that HT in such a way, this differential operator can be written as a derivative, a single derivative of a function. In this case, only in this case, if we can find HT, your differential equation reduces to d by dt of h is equal to q. You see, once you do this one, your problem is solved, because it is an integral calculus problem that will give you immediately your HT is equal to some constant plus integral of qt dt. You see. So, you have that one. So, the question is that can you find that one? In general, that may not be possible always, but the form suggests you that. So, in general may not be possible, because we do not know. In general it may not be possible. So, that is where the concept of integrating factors coming into picture. Integrating factors, normally written in books, and teachers in colleges use this notation always, integrating factor. The idea, can we multiply, can we find the given differential equation may not be exact, but the question is that can we find some mu t so that mu t, if after multiplying mu t the differential equation or the operator plus mu t into p t y t, can we find so that this differential operator is exact? Can you do that one? Because when there is, it looks like a kind of product form. So, you see this is mu t into dy by dt and y into y, this the intuition behind the reasoning, intuitive idea behind is that this is something in a product form. So, you have dy by dt here, yt here. So, if you want to satisfy d by dt of some product, so that gives us a hope that if you can find some sort of this as the derivative, this gives you a hope to consider. You have to see that it is not that blindly feeling that, to consider d by dt of mu t into yt. So, if you consider this one, it will immediately tells you that the first term you get it dy by dt plus you want it d mu by dt into yt. But what do we want? We want in such a way that if we can write this differential equation is this equation. So, if it is possible to find mu in such a way that this d mu by dt coincides with this one, if we can find d mu by dt and this one equal, then this entire thing, let me use another color, the entire thing going to be equal to this one, and we get an exact differential equation. So, by multiplying, if the given differential equation is not exact, it may be possible to make it exact by multiplying that equation. So, what is the advantage making it exact? The moment you make the differential equation exact, it is going to be a integral calculus problem. So, you want to solve it. So, would like to solve d mu by dt equal to mu t pt. Do you see? Now, you recognize this one. What is this problem? This problem, if you look at it, it is a homogeneous linear first order equation, which is what we were discussing so far. So, our non-homogeneous linear first order equation eventually reduced to a solvability of the homogeneous linear equation for mu t. And once you solve this homogeneous linear equation mu t, you can use that mu t as a thing, and you know that this solution exists. So, this is nothing but the mu t is a first order linear homogeneous equation, you see. So, you are reducing to the case. So, the non-homogeneous case eventually reduced to a first order linear homogeneous equation, and then when you find mu t and multiply that one, it will reduce to an integral calculus problem. So, earlier the first order reduced essentially to an integral calculus problem, here we have to do it in 2 steps. Okay. So, how do I write it? I can write immediately, this already you have written mu t. So, I can write a mu t with a constant does not matter, because I am interested in only an integrating factor. Get one integrating factor, you can always get another integrating factor by multiplying by a constant. So, this going to be immediately is going to be integral of, let me write down immediately, it is going to be mu t is equal to integral, this we are already know how to solve it, integral of pt dt. Okay. You see, so you have an integrating factor by solving the homogeneous equation. You have to understand these steps. I am writing here one of the very familiar thing which we usually try to write it in blindly. We want to say that there is nothing we are deriving, nothing blindly writing it coming, you are reducing your equation. So, you have your mu t, let me write down mu t once again e power integral of pt dt, and then our differential equation reduces to the first thing you are multiplying mu t into dy by dt, let me mu t you have to into pt yt, you have to multiply the right hand side also, you should not forget it, mu t into qt, you see. And this is what we have done now. With this choice of mu t, this will become d by dt. You cannot take arbitrary mu t, you have to have this one. This This form you are all familiar probably, but then you see mu t into y t. So, you have the integral, that is your h t, mu t into q t. So, this is an integral calculus problem. This is an integral calculus problem. Integral calculus problem. And you can immediately write down your mu t is y t is equal to a constant if you want it, plus integral of mu t q t. So, you see, and then you take mu t is an exponential thing and mu t is greater than or equal to 0, it can never vanish. So, that implies your y t is equal to 1 over mu t some constant into integral of mu t q t. Am I right? Yeah, that is the formation. So, you have to, if you substitute mu t, you get your solution. Constant can be determined by looking at the mu t is this one. So, 1 by mu t is e power minus integral of p t dt c plus integral of q t e power integral of p t dt. The interesting thing is that you do not have to remember any of these things. It is anyway, it is a one step calculation. We have done this calculation to show you that this all these integrating factors and everything is coming very naturally. So, naturally to you. So, you do not have to worry about that one, and probably in the next class I will recall this once again and maybe show you 1 or 2 examples in the next class. But to conclude this lecture, in the example you have to send them. So, we have the so let me conclude. First we have solved the integral calculus problem, integral calculus, solving nothing like dy by dt equal to f of t, and second step linear homogeneous equation, that is equal to dy by dt e plus pt y is equal to 0. So, this reduced to a integral calculus problem. That is what you have essentially done. If you do this one, what you have done, log mod y dy by dt by y, it does not matter. So, you have solved it. So, you have a solution, and then linear non homogeneous, you have this equation dy by dt plus pty is equal to qt. This you have done in 2 steps. 2 steps. 1, find an integrating factor, mu t, and this is obtained by solving a homogeneous equation. With that step, this is a step 1. In the second step, our ODE, this equation ODE 3 reduces to an integral calculus problem. And this is what we have done, and thus the complete linear first order non homogeneous problem which takes care of everything is completed. So, what I will do in the next class, we will introduce the concept of exact differential equations, and we will understand that in the next lecture. Thank you very much.